I feel like we have a forum, so we can start. So hi, everybody. Thank you for coming. My great pleasure today to introduce Dan Wilson, who is an associate professor of electrical engineering and computer science at the University of Tennessee. He received his PhD from UC Santa Barbara and followed that with a postdoc at the University of Pittsburgh prior to going to UC Knoxville. He is the recipient of an NSF Career Award and a Scion Life Sciences Early Career Prize, recognizing his work on public oscillator theory. I'm excited to hear this, so without further ado, please help me.
Thank you for the introduction and for the speak today and to come out and visit Northwestern. So this talk is going to be about limit cycle oscillators, some recent strategies that we've developed for representing these highly nonlinear systems in a reduced order capacity, and some applications that this enables that you wouldn't be able to do just worrying about the full system equations. There's a lot of oscillatory systems that occur in nature. One that I think a lot of people are intuitively familiar with is their own circadian rhythms. So these are evolutionarily advantageous for people to be able to anticipate and respond to predictable changes in their environment. So for instance, during the day, you're awake, at night, you're asleep. And in humans and other mammals, the suprachiasmatic nucleus is responsible for maintaining your circadian oscillation. So this is located in a little patch of tissue just behind your eye that's responsible for taking in information about that's happening externally, like for instance, is there light or dark and other things, and maintaining a 24-hour cycle that's entrained to the external light and dark cycle. Now, many people have done a lot of great work looking at the underlying behavior of the system, all the different gene regulatory networks that contribute to circadian physiology, and that's useful in a lot of applications. But sometimes you're just interested in the timing of these oscillations, not necessarily the underlying state variables. And if that's the case, you can take, say, for instance, a circadian rhythm and reduce the dimensionality according to a phase reduction, which looks something like this. So for phase reduction, you say, again, I care about the timing. I'm going to define a new variable theta, which is on a circle, ranging usually between 0 and 2 pi, or 0 and t, where t is the unperturbed natural period of the system. You can scale your phase so that in the absence of any input, d theta dt is equal to omega, just a constant depending on what the unperturbed frequency is. And if you want to think about, say, the response to external inputs, such as light, you can add a phase response curve z multiplied by the input itself. And so I think most people are at least intuitively familiar with their own circadian phase response curve to light. For instance, light coming through your TV or computer screen late at night is going to delay your circadian rhythm, and you might have a hard time falling asleep at a normal time. That exact same light coming through your window early in the morning is going to advance your circadian cycle and wake you up. And you can do tightly controlled laboratory experiments, shining light in people's eyes at different times of day and measuring this change in their circadian phase, and back out a phase response curve to light. And it looks like you would expect, where in the morning you advance the circadian phase with light, at night you delay the circadian phase with light. So now kind of keeping in mind that you're taking a very complicated system, representing it as a one-dimensional ordinary differential equation, you kind of expect there's going to be some limitations associated with this strategy. And this slide is just illustrating some of those limitations. Is that while I can do my experiment, I can measure a phase response curve, but that phase response curve is going to look different depending on what input I applied to measure those phase response curves. So this is just another experimental example, applying a relatively large duration light that's bright and measuring the phase response curve, we get something like this. A shorter duration light gives me a phase response curve that looks like this, and a smaller magnitude light gives me yet another phase response curve. So the question is, well, if I want to do this phase reduction, what response curve do I use? And the answer is, well, it's more complicated than that. None of these are right or wrong. It just depends on the underlying dynamics of the system, which we'll talk about in just a second. So this simple phase reduction strategy, you want to get a bit of a better sense of when does it work and when does it fail. Zooming out a little bit, just thinking about a planar two-dimensional system. Two variables v and n here. This system has a limit cycle shown in gray. And along this limit cycle, I can define a phase between 0 and 2 pi in this case and scale so that in the absence of input, d theta dt is equal to omega. I can extend phase to the base of attraction of that limit cycle using the idea of isochrons. And isochrons just say two initial conditions on the same isochron have the same asymptotic convergence to the periodic orbit. So for this planar system, I'm calculating numerically all of the isochrons shown as different colors, and these black lines give me level sets. So of course, two different initial conditions on the same isochron are going to come together until they end up at the same spot on the periodic orbit in the limit as time goes to infinity. So you kind of have the topology of this problem, and then I can think, well, what if I do a phase reduction? I can do that to define my phase response curve as the gradient of the phase evaluated along the periodic orbit. And so what I've gotten from this is I go from a two-dimensional system, or more generally an n-dimensional system, to a one-dimensional reduction that looks like this. But for that, I have a very large restriction where I have to say I have to stay very close to this periodic orbit for my phase reduction to work, because otherwise, if I get pushed into here with a large input or pushed in this region with a large input, I'll still get a prediction for what the phase is going to do, but it's probably not going to be right because I've thrown away any information about what happens in here, what happens out here. So the question becomes, and what we thought a lot about over the past couple of years is, well, how do I get, say, a better phase reduction? We like phase reduction. Going from a high dimensional system to a low dimensional system is great. But for practical applications, I throw away too much information. But I want to think about, well, can I augment phase reduction with some additional information and still get something that's analytically tractable, or something that I can still formulate and solve nonlinear control problems? And the second is, what are some applications that I can do with this information? Again, I don't just care about giving a representation for my system and matching my data. I want to use that further and do some type of analysis or control on my network that I couldn't do otherwise. All right, so just talking about one strategy we've come up with that tends to work pretty well. I'm going to assume that I have the following system. So general n-dimensional system, dx dt is equal to f of x plus u of t. So f is the dynamics, u is an additive input. I can also put the u inside here so it no longer has to be a phi, but just for the purposes of explanation, I'm going to have it with a plus sign out here. I'm going to assume that this system has a periodic orbit, x gamma of t, in the absence of input. And I said a moment ago, okay, I need to have some additional information about some amplitude coordinates. Again, phase just gives me timing, but I need to know what happens out here and here. I need some kind of amplitude coordinate. There's a lot of different amplitude coordinates that I could choose, but one that ends up being useful is to use the isostable coordinate framework. So isostables can be formally defined as principal sets of Koopman eigenfunctions. They have this nice property that in the base of attraction of the limit cycle, I have my isostable coordinate just having some exponential decay, where this kappa j here is the flow k exponent associated with the monodromy matrix of that periodic orbit. To linear orders of accuracy, these are the same as flow k coordinates. But what's nice about isostable coordinate is I can extend this beyond the linear regime to the nonlinear base of attraction. But nonetheless, if I want to think about my state as a function of time, it's just going to be wherever I am on the periodic orbit, plus a linear combination of flow k eigenfunctions multiplied by my isostable coordinates. Again, I can do this expansion to higher orders, but to linear order of accuracy, this is what I get. Oftentimes, when I do this transformation, I'm also going to end up with some of my isostable coordinates being rapidly decaying. These kappa terms here are often negative and large in magnitude. So they decay exponentially fast, very quickly, and I can get away with just assuming that they're equal to zero. So I don't have to consider all n minus one of these. I can generally consider just a small subset in my reduced order modeling. So with this in mind, again, we have this idea that if I use a single periodic orbit, if I give an input that drives me too far from that periodic orbit, I'm going to end up with a reduced order model that's not accurate anymore. So perhaps I could start to think about, well, maybe I could consider a family of periodic orbits, not just a single one, and use that for my reduction. And this is kind of a caricature of a strategy I'm going to describe in a minute. So for this example model, with a three-dimensional system, often used as a gene regulation model, these three variables here. And I'm close to a supercritical Hopf bifurcation if I view LC as a bifurcation parameter. So taking LC equal to 0, I end up with this periodic orbit, but I get a bunch of different periodic orbits that foliate phase space because, again, I'm close to that supercritical Hopf bifurcation. And so I want to think about, well, maybe I can use this family of periodic orbits in order to get a better reduced order model. And so one, again, cartoon of this is saying, well, okay, suppose I have two periodic orbits, one blue and one red. If I start off at initial condition very close to that blue periodic orbit, again, I could do my phase reduction and get a good approximation. But as I start to get further and further from that blue orbit, I'm going to have a worse and worse approximation. But perhaps I'm getting closer and closer to the red orbit. At some point, it might make sense to convert my coordinates to those associated from those associated with the blue orbit to those of the red orbit, limiting the magnitude of my amplitude coordinates and thereby ending up with a good representation for the system. I'm never too far from a single periodic orbit. So this is kind of a cartoon schematic of what you can do for a discrete set of periodic orbits. I can also do this with a continuous collection of periodic orbits, which I'm going to show on the next couple of slides here. So again, the idea being, I'm going to assume that I have some nominal collection of parameters. You can think of this perhaps as a bifurcation parameter, where I get different periodic orbits for different values of P. But these are the actual state dynamics. This parameter doesn't need to change in time. I'm just going to use the periodic orbits for different values in order to, in reference to my reduction for my limit cycle oscillator. So instead of this actual nominal dynamics, I'm going to consider the following system here. So x dot is equal to f of x comma p plus u eve here. So this again is going to be different values of P give me different periodic orbits that I can consider the system relative to. And for UE over here, I say, okay, I add my input, I add what my actual dynamics are for the system, and I subtract off this kind of shadow system, f of x comma P. So I recover exactly what I had over here. I just call this my input, and this is going to be what I'm going to use to do my reduction relative to these periodic orbits. So first, a few assumptions. Again, for all allowable P, I'm going to assume that I get a stable periodic orbit, that I can take that periodic orbit and do a phase amplitude reduction. So I have theta dot is equal to omega plus z times u, my standard phase reduction. I also have a reduction of my isostable coordinates as well, so something similar. I'm also going to assume some level of differentiability with respect to my parameters, because I'm going to take some partial derivatives in just a second. And also that I have some amplitude coordinates that I can truncate because they decay rapidly. So when I do this, I can change variables to my phase and amplitude coordinates. And instead of simply being functions of my state, like they are in standard phase reduction, they're also functions of this adaptive parameter P, again, which is telling me which orbit do I want to consider the dynamics relative to. I just get this from the chain rule over here. And then the question is, well, I need to figure out what are these equations? How do I relate these to things that perhaps I already know? Well, a couple of these terms are easy. Again, these red and blue terms are exactly what we get if we hold this parameter P constant. This is the standard phase amplitude reduction that people have been working with for quite some time now. So we already know how to calculate these things from a numerical equation. I know how to calculate a phase response curve. I know how to calculate the gradient of my isostable coordinates, my isostable response curve. I just have these other remaining terms here, which tell me, for instance, this gives me how does the phase change when I'm adjusting my reference periodic orbit P by changing this parameter, or by changing the parameter P here. And likewise, this tells me how does my amplitude coordinate change when I adjust this parameter P. It turns out I can also calculate these things, and I end up with something that looks familiar in terms of some of the things that I already know. So for instance, the partial of theta with respect to the ith parameter ends up being equal to -1 times how does the periodic orbit change when I change the ith parameter, and dotted with the phase response curve, which I already know. I can calculate this for all of my parameters in my system. I can also do the same thing for my amplitude coordinates until I end up with this adaptive reduction, which looks similar to the phase reduction that we had earlier, but I have some additional terms that once again ultimately allow me to consider larger magnitude inputs. So again, I have my natural frequency as a function of P, my phase response curve as a function of P, this effective input, like I mentioned earlier, this term here, which tells me how does the phase change as this adaptive parameter P changes. I get a similar equation for my amplitude coordinates. I also have this free parameter, P dot, where again, this is telling me I have different periodic orbits in my system. And I can change this freely, ultimately with the goal of limiting these amplitude coordinates. If I can make sure that these amplitude coordinates are small in time, I'm always going to be close to at least one periodic orbit so that I get a good approximation for the dynamics. So that's the general idea behind this. And just a key point, I can control GP. I can choose that to be whatever I want. Again, I'm trying to tune this so that my state is close to one of my underlying periodic orbits. And if I can do that so that the magnitude of my amplitude coordinates remains small, I'm going to get a reduction that's order epsilon accurate regardless of the magnitude of my input, which is different than most reduced order modeling strategies for oscillatory systems. Usually you have to have a small magnitude input or restrict the frequency somehow to get an accurate reduction. But this just allows me to give whatever input I want. As long as I can tune this parameter P appropriately, I can get an accurate reduced order model. So that's the general idea. So we can try this. One of the first things we tried was a population of 10 coupled oscillators. Overall, the dimension of the system was 40. We wanted to say, okay, could I take this 40-dimensional model and reduce it to something smaller? In this case, I end up with a 5-dimensional model using this adaptive phase reduction strategy. I can see the actual model. If I plot the average of one of my variables, gives me these gray lines. And the adaptive phase reduction gives me a blue line in response to its forcing. And so I end up with something that's pretty close and comparable to the behavior of the full order system. Comparing this to some other state-of-the-art strategies, I have my standard phase reduction. I have what's called extended phase reduction, which is like this proposed strategy, but doesn't include the amplitude coordinates. I can also do Taylor expansions. None of these strategies work very well. The only one in this case that we end up with a good model is this adaptive phase amplitude reduction. I can see it from these traces here. I can see it from the deviation between the actual phase of my system and the phase that my reduced order model predicts. But of course, again, I don't care about necessarily just getting good representations of the behavior. I have no problem simulating a 40-dimensional model or even larger models like from on a supercomputer, no problem. But what I really care about is that these reduced order models enable analysis that I would not be able to do otherwise. But once you have a good model, then you can say, okay, maybe I can start to define some long-term control strategy or some try to understand the behavior of my system better in a way that I wouldn't be able to do with just working with the full system of equations. So one of the first things we thought as well, maybe we can try to think about a jet lag mitigation technique. So for jet lag, as you're probably aware, if you hop on a plane across the Atlantic Ocean, maybe a plus 6 or 7 hour time advance, the environmental time changes immediately. But your body's circadian clock takes some time to recover. And if you could come up with, say, a good light seeking or light avoidance strategy in order to get your body's internal clock to match the external light dark cycle, you could mitigate jet lag. And if you don't do anything, well, you'll recover to the new 24-hour light dark cycle, but it'll take some time. So these figures here are showing the results of formulating that problem according to an optimal control problem with the calculus of variations approach and solving it for the different models. So for instance, this panel A over here says, if I don't do anything, and say, for instance, I have a plus 10 hour time advance, for the model we're using, it's going to take about 300 hours to fully recover that new 24-hour time zone. The same negative 10 hour time delay is going to take about 100 hours to recover. So it takes some time, comparable at least with what you might experience in real life. I can also formulate an optimal control problem, find a light seeking or avoidance strategy that says, well, I want to try to recover more quickly than I would otherwise. And we do this two different ways, with this proposed adaptive reduction and with the phase isostable reduction, which is not particularly well suited to large magnitude inputs. I can formulate and solve both of these problems, but only one's going to work when I actually apply it to the full order model. So again, for a +hour, 7-hour time advance, I get a solution for this model that's not particularly well suited to large magnitude inputs. I get a different solution for my phase amplitude reduction, likewise a similar thing for this negative 10-hour time delay, but only one works when I actually go and apply it to the full system. So the adaptive reduction works as intended. This phase isostable reduction, sometimes it does better, but sometimes in fact it just does worse than actually doing nothing. So I can see it from this chart over here. It's better for these lines to be lower because I recover faster. But I can also apply this input to my system. One of my variables, this is the target that I'm going with for my +7-hour time advance. I get very quickly to that target for my adaptive reduction. Again, I can solve my optimal control problem for my phase isostable reduction, but the actual answer doesn't give me results that work because, again, this reduced order model isn't very good for representing the behavior of the system. And this is compared to just doing nothing and waiting for the 24-hour light and dark cycle to recover. So that's one of the first applications we consider. We tried this for some other models. And one interesting thing that's kept happening is, again, we use this phase amplitude reduction. We calculate these reduced order models for large populations. In this case, we were thinking about a model of 3,000 coupled oscillators, as might be relevant to thinking about coupled oscillations of neurons in a superchiasmatic nucleus. And what we found is that when we want to give large phase shifts, we always found that there was some transient desynchronization that happened before we end up resynchronizing at the correct phase. So you can see this from this application of this control algorithm. I give one pulse from this raster plot. I start off very highly synchronized. I transiently desynchronize before giving another pulse and resynchronize to the correct phase.
Do you have noise in there?
There's noise, yeah, there's noise as well. So there's a coupled mean field coupled with noise. I can also look at the system with a rotating Karmoto order parameter and a rotating reference frame, where this traversal through the middle indicates this desynchronization. I get something similar for an 8-hour time delay. An initial pulse that desynchronizes, followed by another pulse that resynchronizes to the correct phase. And we tried a bunch of different models, and we kept seeing this general phenomenon. We're not mandating desynchronization first, it just kind of happens for these models. So we wanted to think about, well, we understand this relationship. Certainly there's some relationship between desynchronization and phase shifting, and we want to characterize this a bit more carefully. So this kind of leads to the second part of my talk, again, talking about some motivation, this phase amplitude reduced equation. We want to think about some connections between re-entrainment and population level synchrony. How can we perhaps understand what we keep seeing in the solution to these optimal control problems? And this is something that also pops up in some of the circadian literature as well. So in this case, mice, which are deficient in a particular gene that make their oscillations in their superchiasmatic nucleus less synchronized, are able to re-entrain to shifts in their light-dark cycle more quickly than mice that don't have that deficiency. So seeing in this figure here, I have a light is on, dark, light, dark, suddenly I have a shift in my time zone, and the mice then need to re-entrain to this new 24-hour light-dark cycle. The mice that are deficient in a particular protein, but the neurons in their SCN are less synchronized than others, tend to re-entrain faster than other mice. We have different results too, where instead of having mice that are deficient in a particular gene, they add a neuropeptide to the system that tends to desynchronize the population of oscillators. And those mice are also able to re-entrain more quickly to changes in the 24-hour environment. And again, related to these results that we saw just a moment ago, there's certainly some level of desynchronization going on here that presumably makes the phase shifting easier for this re-entrainment problem. We want to think about, can we understand this connection a little bit better? So one thing we started thinking about is, okay, let's just give me a general model for a large population of coupled oscillators. So I have from I is equal to 1 to n oscillators. We have a variable X and Y. All of the coupling and noise happens in the variable X. These Y's are just auxiliary parameters that give a limit cycle for these systems when I don't have any sort of coupling or other perturbations. D in this case is the noise intensity. Sigma is the coupling strength. For the moment, we'll assume both of these are small order epsilon terms. So if each of these elements have an intrinsic limit cycle, I can do a preliminary phase reduction. So I can say the phase of my ith oscillator is equal to omega, the natural frequency. I have my phase response curve, and then I have all of my inputs. So I have my noise, I have my mean field coupling. And these are all coupled in an all-to-all fashion. Looks like this. All right, and if I can do an additional transformation and say, well, in the large N limit, instead of worrying about all of the individual oscillators, maybe I can just worry about the probability density. And I can make that transformation with the Fokker-Planck equation. So I get a term that looks like advection. I get a term that looks like diffusion. I expand everything and get this mess over here. But nonetheless, okay, now I'm worrying about probability distributions and not necessarily the dynamics of the individual oscillators. And to make my life a little bit easier, I'm not going to do analysis on this partial differential equation. I'm going to discretize it with a finite difference approximation where now I have n elements, but the idea is the same. I have some advection term, some diffusion term, and I want to think about the behavior of this model as I change different things in it. So one thing, kind of some preliminary analysis. Again, I've said that my coupling and my noise are order epsilon terms. Well, in the limit that both of those go to zero, I just get the advection equation over here, which has been studied over and over. I can say, well, what are the eigenvalues of that advection term? I get one on the imaginary axis, which gives me a sense of the average value of the probability distribution, which has to integrate to one. So that's never going to change. But I have these other two eigenvalues, which are pretty close to the imaginary axis. And as I increase the coupling, those eigenvalues end up eventually crossing the imaginary axis with Hopf bifurcation. And as the coupling increases, I start off with a probability distribution, which is not very synchronized. I go past that bifurcation, and now I have limit cycles, or if I give different snapshots of those limit cycles in time, I have growing synchrony as I go further and further to the right across that Hopf bifurcation. I can do some perturbation analysis, once again, assuming that my noise and coupling are small, and take a look at exactly when that Hopf bifurcation occurs, so that the coupling is going to have to be proportional to the noise intensity. I can also look at the criticality of that bifurcation by looking at the second and third order term. Now, this computation was a little bit more difficult. What I'm after is the Perturbed coefficient telling me whether or not this is a supercritical or a subcritical Hopf bifurcation. And with a few steps, you can show that, well, focusing on the phase response curve of the system. Again, the phase response curve tells me the influence in response to perturbations. If I take a look at the Fourier coefficients of that periodic function, as long as the first Fourier coefficients are sufficiently large relative to the others. In other words, as long as I don't have some degenerate case where I have a phase response curve that's highly oscillatory, which typically doesn't happen in practical applications, then I'm going to end up with a supercritical bifurcation and where the first Lyapunov coefficient is less than zero. All right, so all this being said, I know that I have my model. I know that I have a Hopf bifurcation, and with a good sense of the phase response curve, I can say that's a supercritical Hopf bifurcation. I'm going to use the Hopf normal form in order to analyze this system. Again, I know that it's supercritical, so usually I have a coefficient here for the Hopf normal form, but I've scaled it out to be -1. The rest of the terms are scaled appropriately. I know that I have a fixed point at r is equal to 0, which is unstable because nominally these circadian models are oscillatory. And I also have this general sense that r correlates with the degree of synchronization in the system. For this unstable fixed point, I have a probability distribution that's flat. As I increase my coupling parameter, I get things that are more and more synchronized. So this value of R gives me some indication of how synchronized is this population of oscillators. And I want to think about this in the context of my earlier results. Again, I keep seeing things that go through the center of this unit circle. If I'm looking at the chromatic order parameter, and I want to think about, well, why is this the case? Or more generally, when can I guarantee that I'm going to get desynchronization associated with these optimal inputs that I apply to the system? And in this analysis, we kept seeing a few different solution archetypes. So again, I have my Hopf normal form. If I just have this going around my periodic orbit and I don't do anything, say I wait 2t, so 2 periods later, I end up in the same spot that I ended up with. But now what if I want to change my phase of oscillation or do some phase resetting? I have a couple options that I could do. One is I could wait some time, drive myself to the phaseless set, which is consistent with this desynchronization, wait there for some amount of time, and then let myself go back at the correct time so that I end up with the correct phase. I have a couple other options too. I could just say, well, I want to slow down my oscillation a little bit, but I want to give weak perturbations that keep me close to my underlying limit cycle. Or I could do the same thing. I could advance my phase by an appropriate amount to end up with the phase being the correct value after 2 cycles. I want to think about, well, what's the cost associated with each of these inputs that we see? So defining the cost as the square of the input that I apply. Thinking about this first archetype where I apply, I have this solution go through the phaseless set, this desynchronized set. Most of the cost is going to be incurred on branch 2. Again, I just wait for some amount of time to get to this point here. I have to drive my system to this phaseless set. Once I get to this unstable periodic orbit, even though it's unstable fixed point, even though it's unstable, it doesn't take much energy to keep it there. And then I let it go, doesn't take much energy, and I let it go to the correct phase. So most of the cost is incurred on this second branch. The associated dynamics on that second branch simplifies to R dot is equal to alpha R minus R cubed minus U, where again, I don't have that sine term on my input because I know that I'm on this left edge over here, and the sine of pi is equal to, I end up with -1 over here. I can define the Hamiltonian for the system. I can calculate extremal solutions for this energy optimal control problem. I end up with the result, the minimal energy along this second branch ends up being proportional to alpha squared, where again, alpha is this term over here for my Hopf bifurcation. So it's going to be positive because the fixed point is unstable. This other kappa term is something that tends to 1 as the total time that I'm going along the second branch increases to infinity. So this is just another scaling parameter. It's generally going to be close to 1, but more importantly, these solutions are proportional to alpha squared. I can do the same thing for my other archetype solutions. In this case, these stay pretty close to the unperturbed periodic orbit. And in that case, I can use my phase reduction. Again, we've said for systems that stay close to the limit cycle, phase reduction works pretty well. So I have theta dot is equal to my natural frequency plus my phase response curve multiplied by my input. I know that the phase response curve for this system is just a sinusoid, which is appropriately scaled and shifted by some of those parameters in the model. I can calculate what my minimal energy solutions are. Again, according to the dynamics of the problem. And then I can compare, okay, well, what do these look like as well? So again, previously I said for a desynchronizing solution, we just kind of have a flat line. It takes me a set amount of energy to get there, and it doesn't matter how much this phase is shifting. But for these small magnitude inputs where I stay close to my periodic orbit, for instance, to interpret the figure, say I start with a phase of 1 and I want to drive myself to a phase of 0 after 2 cycles. I don't start too far from there, so I just slow it down a little bit. So this is the amount of energy it takes. If I want to shift my phase by 3, it takes more energy. If I want to shift my phase by 5, it takes more energy. And in fact, if I start with 5 and want to shift it over here, I might as well just complete the revolution and go all the way around the circle. So if I want to do a phase advance, it takes this amount of energy and so forth. At some point, these two are going to meet in the middle. I get different qualitative solutions, whether or not I give a phase advancing input or a phase delaying input. But for instance, if psi here is equal to pi, then I end up with this, say, at the same location, just with one extra revolution or one less revolution. But again, kind of this general sense of how much energy does it take to solve this problem. So now I have estimates for these archetype solutions. I want to compare it to what the actual optimal solutions are when I apply a second strategy, which is just use dynamic programming. This is a two-dimensional model. I can calculate what the actual optimal solution is accurately, just with dynamic programming. And it turns out that I end up with actual minimal solutions, which match up with my theoretical predictions here. So using this Hopf normal form, parameters given here, I set up this phase advancing or this phase shifting problem. And depending on what the phase shift that I want to give is, I follow this weak resetting branch. At some point, this branch that says drive myself to the phaseless set, wait there for a set amount of time and let it go becomes more optimal. And finally over here, I have this phase advancing branch that's more optimal. So I can see it in these figures over here. If I give a small phase shift, I stay close to my limit cycle. If I give larger phase shifts, I kind of go once around, go to the middle, and end up letting it go at the appropriate phase. And then if I get all the way over here, again, the phase shifts aren't that much. So I have my value of R and staying close to the unperturbed limit cycle. Okay, that's just Hopf normal form. I want to see, can I get a similar result when I actually apply this to a coupled population of oscillators? Does this general intuition follow with the optimal control solutions for this system? So I take a population, in this case of neurons, have a mean field coupled, and try to solve this exact same optimal control problem. I fit the terms of my Hopf normal form using some simulation data, and I get behaviors that are similar. So again, if I want to do a shift in my phase that's pi, so kind of the largest shift that I can possibly give, I end up going through the center here to something that's desynchronized before coming out the other end at the correct phase. If I give smaller phase shifts, I have something that stays closer to the outer edge here, indicating less synchronization. Again, this is another smaller phase shift. I don't end up desynchronizing nearly as much as I do for these large phase shifts. Again, these are calculated from a dynamic programming approach using a model predictive control algorithm, but nonetheless, we follow the general behavior of these solution archetypes that we calculated the energy for, where I get more desynchronization as indicated by the order parameter as I give larger and larger phase shifts. I can also calculate what is the actual energy required to achieve this optimal control goal. And I have something that's, again, it qualitatively matches. It's not perfect because, of course, this is a large population of oscillators. I'm representing this in the Hopf normal form to get these values. But nonetheless, qualitatively, we have this slow ramp up, this plateau here that's associated with more desynchronization, and this slow ramp down. So kind of the overall big picture takeaway of this analysis is, again, I wanted to think about how is desynchronization related to this notion of phase shifting. We have these theoretical amounts of energy required for these solutions. When I have small shifts in the phase, either weak resetting is going to be more energy efficient because I don't have that much to go. But if this flat line here associated with the strong resetting where I drive myself to the phaseless set, wait there some time, and then drive myself to the correct phase is lower than these peaks over here, I'm going to get solutions where I have strong resetting. I can calculate exactly when I can expect that to happen. And in general, this line here is going to have some solutions that are below this peak here when both of the following are true. Just general heuristics from this analysis. The first is that I'll have some desynchronizing solutions when the relaxation rate governed by alpha is sufficiently slow relative to the natural frequency, and that the required phase shifts are large, in which case it's going to be worth it to desynchronize first before I resynchronize at the correct phase. Otherwise, I'll just give myself small perturbations and get there and get to my target without having to drive myself all the way to the phaseless set. And again, this jives with earlier results where we're doing this adaptive phase amplitude reduction, seeing for these large magnitude inputs some initial desynchronization before resynchronizing, even though we weren't concerned at all about how synchronized this network is. It just fell out of the optimal control problem for this jet lag mitigation strategy. But just for a few concluding remarks, standard phase reduction has been used forever. There's been a lot of really interesting results for systems. In fact, by some people in this room have used that strategy to get some cool results for populations of oscillators. But it doesn't work when I apply large magnitude inputs particularly well. And so the question becomes, well, what can we do? Well, we can add more information about the amplitude coordinates to still get a reduced order model that performs reasonably well without sacrificing too much accuracy in the system. So I get something that's analytically tractable, or I can formulate a computationally tractable control problem to get results that I would not be able to otherwise if I was just working with the full order system. And then, of course, other strategies, for instance, you can consider normal forms of bifurcations and do some analysis like we saw to think about this connection between synchronization and phase resetting. Here's just a few references for some of the things that I've talked about today, students that have helped with some of this work, and of course, funding information. And I'd be happy to take any questions.
So is the model-based control that you're using an energy minimization
That's right.
strategy? Okay,
Yeah.
so it's consistent exactly with the idea that's what I want to say.
Yeah, exactly. So again, there's this trade-off. I mean, it takes some work to get to the phaseless set, but once you're there, you can go anywhere. And so the question is, how much energy are you expending to get to the phaseless set relative to how much energy would you expend otherwise just sticking close to the periodic orbit?
And also it seems like the energy depends really on how far you want to move, how much of a phase shift you want to
Yeah.
move, right? So
Yeah, that's exactly right. I mean, it's going to take me, if I'm looking at a rotating reference frame, it's going to take me more energy to get, say, or less energy to get from here to here to say if I wanted to go from here all the way around the circle this way. That's going to take more energy. So again, at a certain point, I'm going to end up with a solution that says, well, forget this strategy. I'm just going to cut straight through the center. And that's going to bring me on a different path. But nonetheless, that path is more optimal than just the weak resetting strategy of staying close to the implement cycle.
part of the reason I ask is from the interpretation of like a biological adaptation control mechanism, like what would it be optimizing and what does this imply?
Yeah, I mean, that's
dangerous questions.
Yeah, that is. I mean, we sort of, from a biological interpretation, if you take a look at some of these recovery times, these are roughly, So for this slide over here, thinking about, again, I travel across the world. I have a 10-hour time advance. That's going to be kind of a rough time recovering from that jet lag. It's going to take me quite a long time. Now, all that's happening really is just I'm letting my 24-hour light dark cycle re-entrain me, and it's probably just it's going to do whatever it does. It's not going to be targeted in any way specific to my circadian physiology. I probably didn't evolve in order to accommodate those rapid shifts in timing. So, I'm going to get there eventually, but it's going to take a while. Now, maybe if there was some way of, kind of pushing me in some correct direction or making small modifications, that'd be great for this problem, as opposed to having to wait a whole ton of time if I just give that perfectly wrong phase shift. Again, for the biology of it, that's a good question. I would say we're probably not adapted for recovering from jet lag. Planes are 100 years or so. It'll take a few years before we get there. But anyway, that's a great question.
Sort of along the same lines. In terms of the jet lag problem, the input cost isn't a major consideration.
Yeah.
But the timing is, right?
Right.
Which is what you're optimizing here. But you could frame the time as a cost itself. Like,
That's true.
Is there a separate problem? Is there a separate solution to the problem where you try to get as fast as possible?
Yeah, that's a great question. Those are harder to solve for these big, highly, nonlinear system reduced order problems, because when you start to talk about minimal time with no, worrying about how much energy do I apply, it's usually bang bang control. Just get there as fast as you can. And even these reduced order models have limits. I mean, again, if I truly have the Hopf normal form, fine, I can solve that problem. But how good is that Hopf normal form going to be at approximating my full order dynamics? If I'm going to hit it with just a massive input, I'm probably going to destroy the oscillation for that actual system. So, you bring up a great point. We sort of chose this energy optimal approach because it kind of gave a good balance between, okay, well, again, I can say I want to get there after, however many hours, but I want to have some idea that I can't just, fry it with a massive input. But yeah, you can formulate it the other way, which may be more relevant to somebody who's suffering from jet lag, but nonetheless, I don't get good answers.
What's the missing ingredient there? Is it that you need to understand like a maximum response, maybe the PRC has some saturation or something?
Yeah, I mean, I think the missing response is, again, so this population is, if this is a coupled population of oscillators, I suddenly hit it with a massive input. I'm probably going to destroy any type of oscillation that I had initially. I'm going to a completely different regime there. So I probably have some other attractor that I have to worry about. And then I have to worry about, okay, well, what's the transition from that attractor to the periodic attractor? And it's much harder. That's probably the missing link. But good questions.
Yeah, I have a question about something in a sense completely different.
Okay.
Which is when you go into surgery and you do full anesthesia and stuff like that. So there is this process that we don't do it in a very controlled way. The surgeons just want you to go under as fast as possible.
Yeah.
But then we know that especially for older people, there is a surgery brain afterwards. So there is definitely some damage about things. And although we cannot think about the entire brain as being an oscillatory system, there are probably some components of it that have some kind of oscillations or something or some states that we would like to be able to preserve. Right? Shut down some things and then bring them back graciously.
Right.
Has there been any attempt to look at that problem from this perspective?
Yeah, I mean, that sounds like a great problem and something that I don't have as much familiarity with. But I mean, that's certainly, again, a situation where minimal energy control, say, would be important. Where you define the energy as smaller amounts of anesthesia or something that I'm not just kind of slamming my system to go to the anesthetized state. I'm sure that you could, formulate some kind of similar problem if you had the right approach.
I'm just kind of suggesting that you do that because in my interactions with surgeons and anesthesiologists, they don't care. And it's like, oh yeah, some people will be having brain damage afterwards. The surgeon has to do the operation within a certain time. And I think that kind of even understanding some of the limits, right? About how fast, I think one of the interesting things that you think about, if you make very big perturbations, it's really hard to know what the consequences are going to be. And all of that approach could be very useful to provide, I think, a foundational base to what we should expect to be possible from anesthesiology or not.
Yeah, I mean, there's similar problems that show up all over the place. I mean, if you have a neuron, you hit it with a large enough depolarizing stimulus, it's going to fire an action potential. Or you could be targeted about it and kind of kick it at the right time and kind of massage it to spike or whatever. So, I mean, without completely destroying the underlying rhythm, the question is, can you do this a smarter way? And the other question is, well, like you mentioned, do the surgeons care?
That's the point of us that are not surgeons, right?
Exactly.
And my intuition is that if you go too hard on these systems, you cause damage. And so if you now have an understanding at sort of a higher level of even qualitative about what is possible or not, that could drive some of the conversation, which I think would be very useful.
Yeah, no, that's certainly an interesting problem I haven't thought about, but
Do you have any thoughts or results on how the optimal solution would change under, like, and this is related to the previous questions, but under different definitions of C, something maybe like incorporating like the time derivative of U?
Different definitions of C?
Like the cost.
The cost. Yeah. I mean, you can define cost, the derivative of U, you can do, where's my definition of cost here? One more. Yeah, you can do the absolute value of U, you can do all sorts of things. Turns out U squared has nice properties that I can solve this problem without worrying too much about it. You'd probably get similar results in spirit, but for instance, if I used, I can calculate exactly what the optimal solution is because I have nice properties of the square of U when I do my when I evaluate my Hamiltonian. Probably get similar results in spirit. They might not have an analytic solution. But you're absolutely right. Why do I use U squared? Do I do it because I can solve that problem? I could potentially use other things. So.
There wasn't anyone else. I'll ask a more minor question. Like in your optimal control for that you had up earlier, that you did numerically, I think you had these sharp corners in it. Is that like a discretization thing, or is there actually something?
Yeah, so I solved this.
I was thinking of an earlier one. One
earlier. This.
Yes.
So again, I didn't talk about too much about the details, but for this optimal controller, assuming there's some baseline 24-hour light and dark cycle, and then I'm going to be applying an input over the course of a single 24-hour period, and then I'm going to turn it off. So that's where these sharp corners come from. So I start doing my control intervention here. I have some continuity, and then I turn it off here. So that's where the sharp corners come from there.
Okay. There was something even before that, before notes. Maybe I missed those. These recovery time graphs. Okay, so not there's optimal growth control here, right? But why is the recovery time
that's so the recovery time, we're defining it here as how long does it take for the cycles to get within 1 hour of the correct phase. And it's hard to define phase a little bit for some of these, I have this coming up and kind of qualitatively, these look the same, but when exactly is this an hour away and when is it not? I mean, it's that's where these peaks come from, because this is, again, I have to make a definition and then I have to just, evaluate it computationally. And just for whatever reason, I can get some of this slop and some of these peaks here. But at least it's, continuous, if not continuously differential.